Good day. I am representing the Group 5 of the MS Modern Geometry class of Central Mindanao University for the first semester of the academic year 2020 and 2021. So, welcome to the world of modern geometry. Okay? By the way, along with me is Mr. Roland James Cabarles and Miss Jody Ann Caspe. And of course, yours truly, I am Eleanor Jones A. We all are taking up Masters of Science in Mathematics Education at Central Mindanao University. Right? Now, what to expect in this video? In this video, we will be proving theorem number 22. We will be defining symmetry groups and translations. Okay, but before that, let's have first a recall on the topics we have discussed last meeting. Alright, we have there isometries. A mapping T of a Euclidean plane onto another Euclidean plane is said to be an isometry before any x and y in Euclidean plane. This holds the distance of the translation of x and translation of y is equal to the distance of the ordered pair containing x and y. Okay. Now, under theorem number 22, we have three stipulations. These are as follows. Number 1. If T and S are isometries, so is TS. Number 2. If T is an isometry, so is the inverse of T. And number 3, the identity map I of the Euclidean plane is an isometry. Okay, so we will be proving them one by one. Now let's start with the first stipulation. The first one states that if T and S are isometries, so is TS. Okay, so here's the proof. If T and S are isometries, then for all x and y, which is an element of the Euclidean plane, the distance of the ordered pair containing the translation of x and translation of y is equal to the distance of the ordered pair containing x and y. Okay? And the distance of another translation of x and translation of y is equal to the distance of x and y. Okay, now, the distance of the translation of another translation of x and the translation of another translation of y is equal to the distance of the translation of x and the translation of y. This follows by definition. This is equal to the distance of the ordered pair containing x and y. Therefore, TS is also an isometry. Okay? Now let's have the second stipulation. If T is an isometry, so is the inverse of T. Okay, here's the proof. If T is an isometry, then for all x and y element of the Euclidean plane, it holds that the distance of the ordered pair containing the translation of x and translation of y is equal to the distance of the ordered pair containing x and y. Now let T inverse be the inversing mapping of T. Then for all x and y an element of the Euclidean plane, we have the inverse of Tx is equal to Tx, and in the T inverse of y is equal to Ty. Okay, this holds the distance of the inverse of Tx, and then the inverse of Ty is equal to the distance of the ordered pair containing the translation of x and the translation of y. And by definition of isometries, this is equal to the distance of the ordered pair containing x and y. Therefore, the T inverse is also an isometry. Okay? Now let's have the third stipulation. It states that the identity map I of the Euclidean plane is an isometry. Okay, here's the proof. If I is an identity map, then for all x and y element of the Euclidean plane, it holds that the identity x is equal to x and the identity y is equal to y. Hence, The d of the identity of x and identity of y is equal to the distance of the ordered pair containing x and y. Therefore, the identity is an isometry. Okay, so that ends the proof of theorem number 22. Okay, now let's move on to the symmetry groups. So here's the definition of symmetry groups. Let F be a figure in Euclidean plane, then the set L of F is equal to the set containing T, an element of I of the Euclidean plane such that T of F is equal to F, and is a subgroup of I of the Euclidean plane called the symmetry group of F. Okay, as an illustration of symmetry groups, here's the illustration for the equilateral triangle. Okay, and here's for the isosceles triangle. Now, in layman's term, the symmetry group basically refers to the original image. So whatever transformation we have, it always end up having the original form. Let's say, for example, the equilateral triangle. If we will flip the equilateral triangle, it will return to its original image, which is the equilateral triangle. Okay? Or the original figure, which is the equilateral triangle. Now let's have the isosceles triangle. We only have one axis of symmetry, considering that we can only do flipping in the isosceles triangle. So if we will flip the isosceles triangle, it basically have the exchange of the vertex y and z. Okay, unlike for the equilateral triangle that we can have flipping, rotation, and so forth. So basically, symmetry groups is the collection of the transformations of a certain figure. Okay, now let's move on to the translations. Translations, in layman's terms, is just the moving of an object. So let's have here the formal definition as provided by the book. Let L be in a line and let M and N be perpendicular to L. The transformation omega M and omega N is called a translation along L if M is not equal to N. The translation is said to be non-trivial. Okay, here's the illustration. Now we have here the vertical line L, okay, with horizontal lines M and N, which are both perpendicular to line L. This basically means that the line M can be a translation of N, and also N can be a translation of M along line L. Okay, basically it moves the line, okay, from a certain direction to another direction. That is just a translation. Okay, translation. Now we have here our remarks. When two lines in Euclidean plane are perpendicular to L, they are of course parallel. On the other hand, when two lines are parallel, there is a line, in fact infinitely many lines, which are perpendicular to both. Okay, so this translation. Thank you for listening. Please reserve your questions in the question and answer portion during our meeting. Once again, this is Elner Jones Ainin telling you, thank you for listening. Good day. God bless us all. Okay.